Welcome! In this session, we'll be tackling an exciting problem, problem number 962, maximum width ramp. Together, we'll explore the core concepts, analyze the problem, and discuss effective approaches to solve it. Let's dive in. In this problem, you are given an integer array called nums. Each element in this array corresponds to a value at a specific index. Your goal is to find a specific type of pair, called a ramp. A ramp is defined as a pair of indices, I, j, where I is less than or equal to j, meaning the first index comes before or is the same as the second index, and the value at nums, I, is less than or equal to the value at nums, j. The width of this ramp is determined by the difference j, I, or the distance between the two indices. Your task is to identify the ramp with the maximum width in the array. If no such ramp exists, the result should be 0. The input will be an array nums with a length between 1 and 50,000, and the output should be the integer representing the maximum width of this ramp. Let's look at some examples to better understand this problem. Consider the first example where the input array is nums equals 6, 0, 8, 2, 1, 5. The output is 4. Here's why the ramp 1, 5 satisfies the given conditions. Specifically, the value at index 1 is nums 1 equals 0, and the value at index 5 is nums 5 equals 5. Since 0 is less than or equal to 5, it meets the criteria for a ramp. The width of this ramp is 5, 1 equals 4. No other ramp in the array has a greater width. For example, while 0, 2 is also a ramp, its width is only 2. Now, take the second example where nums equals 9, 8, 1, 0, 1, 9, 4, 0, 7, 6. The maximum width ramp here is 2, 9, where nums 2 equals 1 and nums 9 equals 6. This ramp has a width of 9, 2 equals 7, which is the largest possible width for this array. Next, let's look at a third example. If the input array is nums equals 5, 4, 3, 2, 1, the output is 0. This is because no ramp exists in this array. For every pair of indices I and j where I less than j, the value at nums, I, is greater than the value at nums, j. Since the condition nums, I, equals nums, j, is never satisfied, no valid ramp can be formed, and the result is therefore 0. Now, let's consider some constraints. The input array can have a length between 1 and 50,000, and each element in the array can have a value between 0 and 1 billion. Given these constraints, your solution must be efficient to handle large input sizes. Finally, let's discuss some edge cases you should consider while solving this problem. For small arrays, such as nums equals 1, no ramp can exist since there's only one element. Similarly, for arrays where all elements are equal, like nums equals 5, 5, 5, 5, the maximum ramp width is simply the length of the array minus 1, because any pair of indices satisfies the ramp condition. On the other hand, arrays sorted in descending order, such as nums equals 10, 9, 8, 7, will never have a valid ramp because the condition nums, I, equals nums, j, will always fail for I less than j. Keeping these cases in mind will help you design a robust solution that handles all scenarios effectively. To solve the maximum width ramp problem, we can start by considering a brute force approach. Here, we iterate over all possible pairs of indices, I, j, where I is less than or equal to j. For each pair, we check if nums, I, is less than or equal to nums, j. If the condition holds, we calculate the width, which is ji, and update the maximum width encountered so far. While this approach is straightforward and easy to understand, it requires comparing all possible pairs, leading to a time complexity of n squared. This makes it impractical for larger arrays, particularly when the input size reaches the range of 10 to the power of 4. Next, we consider an optimized solution using a monotonic stack. The intuition here involves maintaining a stack that stores indices in a decreasing order based on their corresponding values in the array. This ensures that the smallest values are prioritized for forming valid ramps. The approach involves two main steps. First, building the stack by iterating through the array and pushing indices where the values decrease, and second, traversing the array backward to find the largest width ramp by comparing the current value against the stack's top. If a valid condition is met, we calculate the width, pop the stack, and update the maximum width during this process. The monotonic stack approach significantly improves efficiency. The reason lies in its time complexity of O, n, as each element is pushed and popped from the stack at most once. This makes it highly suitable for large input sizes. However, while the method is efficient, it does require a solid understanding of how monotonic stacks operate, especially the mechanism of maintaining a stack in decreasing order. Another alternative is an approach that leverages sorting. Here, we create a list of tuples containing each element's value and its index. We then sort this list by value in ascending order. Once sorted, we traverse the list while keeping track of the smallest index encountered so far. For each tuple in the sorted list, we calculate the width using the difference between the current index and the smallest index seen so far, updating the maximum width as needed. This method has a time complexity of O, n log n, due to the sorting step and requires O, n, additional space for the auxiliary list. While easier to grasp conceptually compared to the monotonic stack, it is slightly less efficient because of the sorting overhead. Given these options, the monotonic stack approach emerges as the most suitable strategy due to its optimal linear time complexity. By focusing on the constraints of the problem, it efficiently handles large input sizes without requiring the overhead of sorting. The stack allows us to maintain a set of candidate indices for I, ensuring they decrease in value, which maximizes the chances of forming a wide ramp. Traversing the array from the end helps directly compute the maximum width without needing additional processing steps. The key observations driving this approach are that the problem requires identifying pairs where nums, I, is less than or equal to nums, j, and the goal is to maximize the difference ji. Smaller values of nums, I, naturally have greater potential to form wide ramps with later indices. While the monotonic stack requires some understanding of data structures, its efficiency makes it the best choice. Comparatively, the sorting-based approach, though valid, is less efficient, and the brute force approach is infeasible for larger inputs. By utilizing the monotonic stack, we achieve an optimal balance between computational complexity and performance. Its linear time complexity ensures scalability, making it the most practical and efficient solution for the maximum width ramp problem, particularly when faced with large input sizes. In this problem, we're tasked with finding the maximum width ramp in an array nums. A ramp is defined by a pair of indices, I, j, such that I is less than or equal to j, and the value at nums, I, is less than or equal to the value at nums, j. The width of this ramp is simply the difference ji. To solve this, let's start with a brute force approach. First, we initialize a variable max_width to 0. This will keep track of the maximum ramp width we've encountered so far. We also define n as the length of the array nums. Then, we use two nested loops to iterate through all possible pairs of indices, I, j. The outer loop iterates through all possible values of I, starting from 0 and going up to n1. For each I, the inner loop iterates through all possible values of j, starting from I and going up to n1. This ensures we evaluate all valid index pairs in the array. Now, within this nested iteration, we check if the condition nums, I, equals nums, j, is satisfied for each pair, I, j. If it is, we calculate the width of the ramp as ji. We then compare this value to the current value of max_width. If the new width is larger, we update max_width to this new value. Once we've evaluated all possible pairs, max_width will hold the maximum ramp width, and we can return this as our result. However, while this brute force approach is straightforward, it comes with a significant downside. Because we are examining every possible pair in the array, the time complexity is O, n squared. For large arrays, this can result in a lot of redundant computations. A key observation here is that many pairs, I, j, do not satisfy the condition nums, I, equals nums, j, meaning we end up performing unnecessary checks. This inefficiency motivates the need for more optimized solutions. One advantage of the brute force approach is that it doesn't require additional data structures, as it directly computes the result by iterating over the array. This gives it a space complexity of O(1). However, the time complexity remains O, n squared, due to the nested loops, which is impractical for larger inputs. When analyzing the algorithm further, we also need to consider edge cases. For instance, if the array nums contains only one element, there's no valid ramp, so the result will be 0. Another edge case is when all elements in nums are the same. In this scenario, the maximum ramp width is simply the difference between the last and the first indices of the array, which is n1. While the brute force approach is a good starting point, its inefficiency in handling larger inputs makes it unsuitable for practical use. To overcome the inefficiency of the brute force solution, we turn to optimized approaches. These methods leverage techniques like sorting, stacks, or two-pointer strategies to reduce the time complexity significantly. For example, sorting can help pre-compute orderings in the array, while a stack can be used to identify and exploit the monotonic properties of the array. The most efficient solutions can even achieve a time complexity of O(n) by avoiding redundant comparisons altogether. These optimized approaches provide a much faster and scalable way to solve the problem, making them ideal for larger datasets. Let's explore these methods in detail in the next section. This Python implementation solves the LeetCode problem number 962, maximum width ramp. The goal is to find the maximum width ramp, ij, where I equals j in nums, I equals nums, j. The solution utilizes a monotonic decreasing stack approach for efficiency. Explanation of the code. 1. Initialization. The length of the array nums is stored in n. A stack is initialized to maintain indices of elements in a decreasing sequence based on their values in nums. 2. Step 1. Build the monotonic decreasing stack. Iterate through the array from left to right, I ranges from 0 to n1. Push indices onto the stack only if the current value nums, I, is less than the value at the index on top of the stack. This ensures the stack remains monotonic decreasing. The stack will now contain indices of a decreasing sequence of elements in nums. 3. Step 2. Find the maximum width ramp. Traverse the array from right to left, j ranges from n1 to 0. For each index j, check the top of the stack. If nums, j, equals nums, stack, -1, it means we have found a valid ramp. Pop the index I from the stack and calculate the width ji. Update max_width if this width is larger than the current max_width. Continue this process until the stack is empty or no valid ramps can be formed. 4. Return the result. The variable max_width holds the maximum width of any ramp found and is returned as the result. Complexity analysis. Time complexity. The first loop runs O(n) to build the stack. The second loop also runs O(n), as each index is pushed and popped from the stack at most once. This results in a total time complexity of O(n). Space complexity. The stack uses O(n) space in the worst case, making the overall space complexity O(n). This approach efficiently handles the constraints of the problem and guarantees the correct result in linear time. This is the Java implementation of LeetCode problem number 962, maximum width ramp. The logic mirrors the Python implementation, utilizing a monotonic stack to track indices of a decreasing sequence. The algorithm builds the stack in one pass and calculates the maximum width in a second pass, iterating backward through the array. Key differences include the use of Java's stack class instead of Python lists and explicit type declarations. This ensures a direct and efficient solution with O(n) time complexity. We start with the example where nums is 6, 0, 8, 2, 1, 5. The first step is to build a monotonic decreasing stack. This stack will help us efficiently track indices of values in nums that decrease as we traverse from left to right. Initially, the stack is empty. At index 0, the value is 6. Since the stack is empty, we append the index 0, making the stack 0. At index 1, the value is 0. This value is less than nums at the top of the stack, so we append index 1, resulting in the stack 0, 1. For index 2, the value is 8. Since 8 is greater than the top value in the stack, we skip appending. The same pattern occurs for indices 3, 4, and 5, where the values 2, 1, and 5 are all greater than the top value in the stack, so they are not appended. By the end of this step, our stack contains 0, 1, which corresponds to the indices of the decreasing values 6 and 0. Next, we traverse nums from right to left to determine the maximum width ramp, which is the largest difference between indices I and j such that nums, I, is less than or equal to nums, j. We initialize max_width as 0. Starting at index 5, the value is 5. This value is greater than or equal to nums at the top of the stack, which corresponds to index 1. We pop index 1 from the stack, calculate the width as 5 minus 1 is equal to 4, and update max_width to 4. At index 4, the value is 1. Since the stack is now empty, we stop the traversal. The final result for this example is a maximum width ramp of 4. Now, looking at the second example with nums as 9, 8, 1, 0, 1, 9, 4, we repeat the process. First, we build the monotonic decreasing stack. Starting with an empty stack, we append index 0 for the value 9. At index 1, the value is 8, which is less than the top of the stack, so we append index 1. At index 2, the value is 1, again less than the top, so we append index 2. At index 3, the value is 0, which is even smaller, so we append index 3. For indices 4, 5, and 6, the values 1, 9, and 4 are all greater than the top of the stack, so we skip appending. This gives us a final stack of 0, 1, 2, 3. Next, we traverse from the right to calculate the maximum width ramp. Starting at index 6, the value is 4, which is greater than or equal to nums at the top of the stack, corresponding to index 3. We pop index 3, calculate the width as 6 minus 3 is equal to 3, and update max_width to 3. At index 5, the value is 9, which is also greater than or equal to the top of the stack. We pop index 2, calculate the width as 5 minus 2 is equal to 3, but max_width remains 3. We continue popping indices 1 and 0, calculating widths of 4 and 5, respectively, and update max_width to 5. The final result for this example is a maximum width ramp of 5. Finally, in the third example, nums is 1, 2, 3, 4, 5. We follow the same steps. To build the monotonic decreasing stack, we start with an empty stack and append index 0 for the value 1. For indices 1 through 4, the values 2, 3, 4, and 5 are all greater than the top of the stack, so we skip appending. The final stack contains only 0. Next, we traverse nums from right to left to calculate the maximum width ramp. At index 4, the value is 5, which is greater than or equal to nums at the top of the stack, corresponding to index 0. We pop index 0, calculate the width as 4 minus 0 is equal to 4, and update max_width to 4. Since the stack is now empty, we finish. The final result for this example is a maximum width ramp of 4. To analyze the time complexity of the solution to the maximum width ramp problem, we can break it down into two main steps. First, we build a monotonic decreasing stack by iterating through the array nums, which has a size of n. During this phase, each index is pushed onto the stack exactly once and is never revisited. This means the work done here is directly proportional to the size of the array, resulting in a time complexity of O(n). Next, we traverse the array in reverse to compute the maximum ramp width. For each index j, we compare the value of nums, j, with the top of the stack. If the condition nums, j, equals nums, stack, -1 is satisfied, we pop indices from the stack and calculate the ramp width. Importantly, each index is popped from the stack at most once during this phase. Since there are at most n indices in the stack, the total number of pops is bounded by n, making this step O(n) as well. Combining both steps, the overall time complexity of the algorithm is O(n). Now let's examine the space complexity of the solution. The primary data structure used here is the stack, which stores indices of a monotonic decreasing sequence. In the worst-case scenario, such as when the array is strictly decreasing, all n indices would need to be stored in the stack. This means the space complexity of the stack is O(n). Apart from the stack, the algorithm uses a few additional variables, including n, max_width, I, and j, all of which require constant space, or O(1). When we combine these, the overall space complexity of the algorithm becomes O(n). Let's compare this optimized approach to a brute force solution. In the naive approach, we would check all possible pairs, I, j, where I equals j and evaluate whether nums, I, equals nums, j. For valid pairs, we would compute the width, ji, and track the maximum width. This approach involves two nested loops, leading to a time complexity of O(n) squared. However, it has a space complexity of O(1), since no additional data structures are used. In contrast, our optimized solution significantly improves the time complexity to O(n) by using a monotonic stack to identify potential left indices and efficiently computing the maximum ramp width in a single traversal. The trade-off is in space complexity, which increases to O(n) due to the stack. This comparison highlights the efficiency gained in time at the cost of using additional memory. Finally, let's analyze the best, worst, and average cases for this solution. In the best case, where the array is already sorted in non-decreasing order, the stack will only contain the first index, and the while loop will execute minimally. Despite this, the time complexity remains O(n), since both steps still require iterating through the array. In the worst case, where the array is strictly decreasing, all indices will be added to the stack during the first phase, and each index will be popped during the second phase. Even here, the time complexity is O(n). For the average case, with a randomly ordered array, the time complexity also stays O(n), because each index is processed at most twice, once during the stack construction and once during the popping phase. To mathematically confirm the big O, note that the first step involves at most n push operations, and the second step involves at most n pop operations, making the total operations bounded by 2n. Since constants are ignored in big O notation, the overall time complexity is O(n). The space complexity, determined by the stack, reaches a maximum of n, confirming O(n) space usage as well. When solving the maximum width ramp problem, there are several common mistakes that can lead to incorrect or inefficient solutions. First, overlooking edge cases is a frequent issue. These include scenarios like empty inputs, single-element arrays, or arrays where all elements are identical. Such cases are often not explicitly considered, but they can cause algorithms to fail or produce incorrect results. Next, incorrect index management is another pitfall. It's easy to mix up the indices I and j, or mishandle how they're updated during iteration. This can result in logical errors, such as skipping over valid pairs or even accessing elements outside the array's bounds. Another mistake is relying on inefficient brute force approaches, like nested loops, without exploring optimizations. With large input sizes, these can lead to time limit exceeded errors, especially when constraints allow 4n to be as large as 10 to the power of 4. Finally, a misunderstanding of the problem statement can derail your solution. For example, some may confuse the width of the ramp with distance or apply incorrect conditions, such as using nums I, nums j, instead of the correct nums I equals nums j. Misinterpreting what the problem is asking for often leads to wrong outputs, so it's crucial to carefully read and understand the requirements up front. Another aspect to consider is space complexity. When solving this problem, neglecting to optimize auxiliary data structures like stacks or arrays can quickly lead to memory limit exceeded errors, especially for large inputs. Now, in interview settings, there are key insights that can significantly improve your problem-solving approach. Always focus on patterns. For array and index-based problems, techniques like sliding window, two pointers, or binary search are often highly effective. It's worth considering these methods before defaulting to brute force. Additionally, optimize early. In time-constrained scenarios, you don't want to spend too long on a naive solution. Instead, aim to quickly transition into discussing more efficient strategies, such as sorting or using a monotonic stack. Lastly, communication is critical. Always take the time to explain your thought process clearly, especially when refining or optimizing your solution. Highlighting the trade-offs in time and space complexity demonstrates a deeper understanding of the problem. If you find yourself stuck, one effective debugging strategy is to manually calculate outputs for small examples. This can help you identify patterns or issues in your logic, which is particularly useful for understanding edge cases and refining your algorithm. Now, this problem also shares similarities with other well-known challenges, which can provide additional context and inspiration for your approach. For example, LeetCode 42, trapping rainwater, and LeetCode 11, container with most water, both involve techniques like the two-pointer method or monotonic stacks to achieve optimized solutions. LeetCode 239, sliding window maximum, is another example where efficient window computations are implemented using a deque. Finally, LeetCode 853, car fleet, demonstrates how sorting combined with a stack can be used to manage complex constraints while maintaining efficiency. Exploring these related problems can deepen your understanding of the underlying techniques and their versatility. There are also alternative approaches to solving the maximum width ramp problem, each with its own trade-offs. The two-pointer technique is highly efficient for sorted arrays but may require pre-processing, which adds an n log n overhead. This method can be challenging to adapt directly for unsorted data unless additional logic is introduced. Another option is sorting combined with binary search. While this improves search efficiency, it also increases pre-processing time to n log n, and often requires extra space for auxiliary data structures. The monotonic stack is another powerful strategy, capable of reducing time complexity to n. However, it demands careful implementation to ensure no valid pairs are missed. Finally, the sliding window approach can be effective under specific constraints, but it may require more complex logic to handle dynamic conditions. Additionally, this method is sometimes less intuitive compared to the others, depending on the problem variation. Understanding these techniques and their trade-offs will help you choose the best approach for different scenarios. Great job! We've covered the maximum width ramp problem, explored efficient solutions, and discussed key takeaways. Keep practicing these techniques to strengthen your problem-solving skills. Don't forget to like, subscribe, and join us for more coding challenges. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!